Hello everyone, Dr. Roberts here from Intro to Electrical and Computer Engineering. This is practice problem 3. It's part of week 10 of fall 2021 lecture slides. Now, if you've been following along, right, we previously started by just finding some equivalent resistances, right, and then finding VA of some resistors. Right, and that was pretty straightforward. And then we went to practice problem 2, where we substituted in a capacitor, and you saw again that once you go into the phasor domain, everything is exactly the same, and then you can solve it the exact same way. Now, if we simplify it again, right, make a slight change, we'll remove one of the resistors, so we just have a resistor and a capacitor. We can do some analysis. And for this circuit, we have 3 questions, right? Determine our V out divided by V in, right? Our transfer function, or our gain, right? B, it asks you what type of filter is this? So this is a filter circuit. And then if we know that the resistor 1 has a value of 1 kilo ohm and the capacitor has a capacitance of 10 microfarads, what is the cutoff frequency? Well, and if I look at the circuit, where do I start? Well, of course, if I see a capacitor, I say, oh man, I got to use phasors and go in the phasor domain. And in practice problem 2, right, we talked about this a little bit more. So if we do that, we can redraw our circuit again. So let's just draw it. And I'll redraw these as resistors, just like this. Now, resistor in the phasor domain stays a resistor, right? So it becomes R1, doesn't change. And a capacitor here becomes 1 over j omega C1. But now we can treat it just like anything else. Now, if I look at this circuit and I want to relate output to input, well, what I see is we have these 2 resistors in series. We have some voltage we want to measure in between them. And so we can use then a voltage divider equation just like before. And so if we do that, we know again that V sub I is equal to V sub in of R sub I over R equivalent, or Z sub I over Z equivalent. Well, for this circuit then, we say, okay, well, Z equivalent is going to be equal to these 2 in series, right? So R1 plus 1 over j omega C1. And we see here, if we're measuring V out that we want to measure, we're actually measuring then across 1 over j omega C to ground. Right, so that'll be our R sub I or Z sub I. So if we do that, we say, okay, well then V out is equal to V in times, okay, on top is going to be what we're measuring across, 1 over j omega C1. And on the bottom is the equivalent, so that's R1 plus 1 over j omega C1, just like that. And, you know, we want V out over V in, so we can then divide through by V in. So if we do that, we get then that, okay, V out over V in is equal to 1 over j omega C1 divided by R1 plus 1 over j omega C1. And that's absolutely correct. However, it's kind of ugly looking, right? So let's multiply by j omega C1 over j omega C1 to clean it up. So if we do that, right, so we do that, then we get that's equal to, so we can write the whole thing, right? So we go 1 over j omega C1 times j omega C1, and this is R1 plus 1 over j omega C1 times j omega C1. So we can distribute this in. And if I come over here then, right, so if I just make an arrow here, just follow along, then what we get there is then we get, okay, this comes on top, so we get j omega C1 over j omega C1 divided by, this multiplies through j omega c1 r1 plus j omega c1 over j omega c1. Right, so when we multiply this fraction, this is going to, the numerator is going to multiply across, so it's going to multiply on this, so will result in this, and the denominator will multiply in, so here it'll multiply on both pieces, so then you can see it multiplies on this and this. And if we look at this, then this fraction is 1, and this fraction becomes 1. So then what that tells us then is that V out over V in is equal to 1 divided by j omega c1 r1 plus 1. And that's part A. Now, if we want to know what's going on with this circuit, right? So part B asks you what kind of filter it is. And by inspection, you may be able to know, right? So what you can see is that the output to the input is connected with a resistor. And so if you had zero frequency, right? So if it's a DC, zero frequency, then a capacitor will charge up and it will become an open, so it goes away. And in that case, we just have a resistor connecting our input to our output, right? So it's going to let zero frequency go through. And so if you have a resistor connecting like this, it's going to be a low-pass filter. However, another way to check it, of course, is, well, let's see what happens, right? So if we let the frequency be equal to 0, then V out over V in is going to be equal to 1 over J times 0 C1 R1 plus 1, right? So this is 0 plus 1, so that's going to be equal to 1 over 0 plus 1, which is equal to 1 over 1, which is equal to 1, right? So let's signal pass, right? So if you multiply this across, to be V out is equal to 1 times V in, so it's going to let the signal pass. So that's good. And so, and then if omega is equal to infinity, right? So let's look at the other end of the spectrum. We see that V out over V in is going to be equal to 1 over J infinity R1 C1 plus 1, or C1 R1, right? I write it the other way. So that's going to be equal to, right, infinity times anything infinity plus 1 is going to be 1 over infinity plus 1, which is equal to 1 over infinity, which is equal to 0, right? So it blocks signal. And there's no energy sources here, so it's just a filter. So in that case, then we can call this and then a passive low pass filter, or low pass filter. So that's part B. Right. And if you're not sure, you can always check, right? Say, okay, what happens to these things? And see, right? You just plug it in and understand. But generally, if you have a resistor connecting output to input, at 0, something's going to flow. Right. Now, part C is asking, then what is the cutoff frequency if we have those values? So then if let me rearrange just a little bit here so we can see all of this all at once. Go gadget focus. Why'd you go out of focus, camera? There we go. All right, so for part C then, right, we know our cutoff frequency equation in hertz. It's going to be 1 over 2 pi RC, and that's in hertz. Where this has to be in ohms, and this has to be in farads. Right, and so we have that R1 is equal to 1 kilo ohm. And we know if we convert it, right, we know that 1 kilo ohm here and 1 kilo ohm here is equal to 1,000 ohms. So it cancels. It says that R1 is equal to 1,000 ohms. And C1 is equal to 10 microfarads. And so we can convert that again to farads, and we see, okay, 10 microfarads there, and we get that 1 microfarad is equal to 10 to the minus 6 farads, which is equal to 10 to the minus 5 when you multiply it out farads. for C1. So we can plug it in. So we say, okay, that means that our f sub c is going to be equal to 1 over 2 pi times 1,000 times 10 to the negative 5. It's going to be in hertz. And if you plug that in, you'll get that your cutoff frequency is equal to 15.92 hertz. Now, as a bonus, if you want to make a Bodie plot just to see what this looks like for a passive filter, it's a low pass filter, right? So it's going to pass things below, but we can mark our cutoff frequency here, which is equal to 15.92 hertz. And we can kind of go where these things intersect. This would be our minus 3 dB point. That's where that happens. Then we have our 0 dB point. That's where the gain is going to be. So we're going to see it's low pass. It's going to go just like that. Right? So you've got a gain of 0 decibels or 1. And then it'll start to fade off. Here's our cutoff frequency. And then this is going to go down at minus 20 decibels per decade. So for every increase of a decade of frequency, you'll drop by 20 decibels. Right? That's kind of the slope of this line. And then higher order filters we'll learn we can do some fancy stuff where we can actually make this steeper, right? Because if you have another signal close by, you may want to block it more effectively, right? This may not be a steep enough hill. But that's beyond the scope of this problem, but hopefully very interesting. And I will see you in the next fractions problem. Cheers.